Welcome to another Fibre Laser Learning Lab. Today we're going to go off on a tangent. We're not going to lose sight of the goal that we're trying to achieve, which is to work out how we thicken the chromium oxide layer on the surface of stainless steel to produce refractive colours. But before we can do that, we've got to understand how we can manipulate that layer with what this machine has to offer. Now, this machine has only got light, which, as I explained to you before, the light energy is like a tsunami wave. It's very powerful, but it has to be and can be controlled, because this is a MOPA laser, which is a pulsing laser, which enables us to deliver very exact amounts of power per pulse. So we've got all sorts of parameters to work with to try and find a way of manipulating the thickness of this chromium oxide layer. Now, the first thing we're going to do is take a quick look at a program that I've written to try and test this machine and at the same time find out what the power is in each one of these pulses. So I'm trying to achieve several things with this program, and I will explain what I'm trying to achieve as we go through. But I think one of the most important things to say is that the program that I'm going to be using is called Lotus Mark. Now, any of you guys out there with a fibre laser will already have a copy of this program, because it's called EzeCAD, but it's written in China. And the one thing the Chinese are not good at is quality control of their software. A piece of software that's completely bug-free will be upgraded, and there will be bugs where there were never bugs before. All credit to Lotus Laser. They have actually frozen a version of EzeCAD for their own use and agreed with the suppliers of the software that they will always receive the same thing. So it will not get bugs coming into it as they upgrade the software, which is an amazing quality control approach, which is reflected in the rest of the design of this machine. Now, you haven't had a chance to look around it, but as an engineer I look at this and I think to myself, everything around this machine is well made and well built. It's well designed. Okay, the actual laser itself comes from China. The head, the lens and the head up here probably comes from China as well. But these are well made pieces. Whereas my experience with Chinese pieces so far, Chinese machines, I mean, I've got a Chinese laser machine over the other side of the workshop there. I've got a Chinese mill here. I've got a Chinese lathe behind me. Yeah. They all work, but the Chinese lathe, I had to spend several hours fixing problems before I could use it properly. The mill was one of the least troublesome things I had from China. The Chinese laser machine, well, over there, you can see my other series and see how many troubles I had fixing all the problems that we encountered with that machine, as well as trying to understand the technology. As I said, this is not a corporate video. I'm not being paid to do any of this stuff. I'm just saying it as it is. So yeah, if we come across problems, don't worry, I shall tell you as well. Now, I don't want to over dramatise what I'm just about to do, but I am prepared. Now, you remember what happened to paper when I exposed it to 10.6 micron wavelength light on the other machine? Yeah, it caught fire. Now you'll understand my precautionary measures. Well, that's very interesting, isn't it? Look, we've marked the front of the paper, but nothing on the back. Hey, I fed you earlier, stop. And absolutely no marks on the anodised aluminium. Well, that's another interesting conundrum, isn't it? We've got the ability to vaporize the ink, which is probably a water-based ink, but we saw water yesterday only absorbing a small proportion of this light, so it was able to force its way through the water and the glass and still have enough energy to damage the black anodized surface. Basically, it was able to evaporate the dye that's in the surface. Not completely, not as complete as it did there, but there was enough energy coming through. So there is a certain amount of energy that gets absorbed by water, and one has to assume that that's what's happened here. Hey, we've got paper behind there. Look, it's absolutely nothing. And yet it has no effect on paper. Doesn't attempt to scorch it, burn it, go through it. We've just discovered something that goes along with the square wheel. Paper glasses to protect you against 1 micron wavelength. Well, here I've designed a matrix to check out all sorts of power and frequency combinations. So it's easy to see if I zoom in on the pattern itself. And there we go. Look, each one of those little marks is a little checkerboard pattern. And here we can see we run about pulse duration from 1 all the way up to 350, doing 16 pulses that are available on this machine. And then what I've done here down the side, we've got a pulse frequency. I've just chosen pulses all the way down from 1000 to 5. Now these are not necessarily the peak power pulses. This is just a range. Now somewhere in there I should be able to find my peak power pattern, but we'll talk about that after we've carried out the test. But before we do the test, let me explain why I've gone for this interesting little pattern. From a distance, as you can see, that looks like a mid-grey. It's not white, it's not black, because it's a pattern of 50% black and 50% white, which your eye perceives as mid-grey. And that's part of the design of the pattern, so that when we look at the pattern from a distance, we can immediately see which parts are burnt well back to white. Remember, we're going to be doing this test on black anodized aluminium, and with black anodized aluminium what we've got to try and do is evaporate away the top surface, which is the sealant, and then we've got to evaporate away the intercrystalline black dye that's hiding underneath the top sealing surface. Now if we remove all of the black dye, we shall get a nice white mark like this. But if we don't evaporate away all of the dye, we shall get something like this. So this has been set up so that it's got a fixed DPI in X and Y, 254. The machine knows that it's got to step down every time 0.1. Okay, so here's our pattern, and that dimension there in both directions is 0.1 millimeters. But of course the problem with this and any other laser machine is it cannot produce sharp corners at this size. This, along with any other laser, is going to have a round beam. So it cannot produce sharp corners. And the claim for this machine is that it has got a beam diameter of 0.065 millimeters diameter. And that's what I've drawn here. That's a 0.065 beam diameter. Now, you might ask the question, why have you drawn it like this? Well, what will happen is, as the software comes in and analyses what it's got to do, it will come across a black pixel and it will turn on a black pixel signal just there. And then it will run out of black pixel just there. And then it will start another black pixel there. And so it will go across and produce lines. It will produce signals to the laser which says turn on, turn off, turn on, turn off. And I don't think this machine knows anything about this little bit here and this little bit here. So the net result is we're going to finish up, I think, but that's what we're going to find out, with a pattern that looks like this. Now it's only going to drive across the center of the pixels because, as I just pointed out to you, I've defined that these lines here are 254 pixels per inch, which makes this dimension here 0.1. So it's going to produce 0.1 lines. even though it comes across black pixels, all it's going to do is see the edge of the pixel and the edge of the pixel and turn on, off, like that. So effectively, even though I've drawn black pixels, it's actually going to draw single black lines, which hopefully are 0.065 millimeters wide. Because this is a pulsing system, I anticipate we cannot change the line width. It is what it is unless we mess around with the focal distance. The whole principle of this test pattern was so that we can have a quick visual check to see whether or not we got 50% grey and 50% white to give us mid-grey. If these marks are not completely white, it means we haven't put enough power in to completely evaporate the black dye. If we get these marks nice and clean and white, then we shall still have approximately a mid-grey look to the pattern. Because if we take a quick look at these two pieces that are hanging out the end here, they're roughly 33.2 units of area. And then when I look at this little red area here, it's 17.5. But of course there are two of those. So two 17.5s is 35, 33. Give or take a little bit, we're not going to get too fussy. We're still expecting to see with this pattern a mid-grey look. Or if we see a completely white look, it means that we've either overburnt these patterns, which I can't really see happening, because we've got to remember the possibility that we have got a beam which has got a power distribution, and I've drawn it upside down this time, but effectively what we've got is got more power in the centre of the beam. I'm anticipating that regardless of the speed at which we run, we shall always get the same position, power level in the beam, which will be that width of line, whatever that width of line happens to be. This is not the same as a continuous power laser, where when you change the speed, you will change the width of the line, because you're only using the very high peak power as you get faster. And as you get slower, you allow more and more of this Gaussian curve to have its burning effect, its power to come in. I don't think that's going to happen here. So I'm expecting to see a fairly constant thickness line. We might see some ghosting of some sort, which would indicate this Gaussian distribution power coming into play. We're going to find out what this machine is actually capable of with this simple test. We can see that the program is very nicely outlined for us, so we don't have to guess where to put the material. So when we catch this in the light right, you'll see that there's a whole band of results across there where the surface has really been badly damaged, and we've worked our way probably even through to the aluminium underneath. We'll have to check it out under the microscope. And we can see that same band when we look at them from a distance, including these three just here. So we'll go and study this stuff under the microscope and see what we can find. Now, I've had a quick look at the first set of results that we've done there before revealing anything to you guys, and there are some fairly interesting, pretty serious inconsistencies in the results. Not what I would expect, and I'm sure these are not results that Lotus will expect when I reveal them to them. The first thing I must do is to make sure that the machine is acting consistently. Now here we are, I've switched the machine off, I've switched the machine on again, I've re-origined the machine and I've reset the program. But we're running the same program again immediately beside the first one so that we can do a comparison. Now the only difference between the two programs is the wording at the bottom. The wording at the bottom says unidirectional on the first one and it should say bidirectional. I've set all the parameters to bidirectional, but I failed to change the wording. So this one has got the correct wording on it. Same pattern. Okay, so I'm now going to examine this under my little microscope, my little USB microscope there, and we're going to take a look on the screen at exactly what's going on. The 1 nanosecond results are supposed to be CW, continuous wave. So as I look down here at the various frequencies that run from 1000 kilohertz down to 5 kilohertz, we should see exactly the same pattern. Lovely. That's just what we expected to see. So we carry on down 800, 700, 600, 500, 400 kilohertz. What's going on there? 300, 2, and we're back to normal. 1, 50, 20, 5, 10 and 5. So we've got lovely consistent results all the way down CW, as you would expect, because that's exactly what it says, constant. And throughout the frequency range we've got good results except at 300 and 400 kilohertz. Now let's take a look at some others. We're not going to take a look at all the results, but let me just jump in somewhere like look at 6 nanosecond. Now, interesting that we've got several things that we can observe on there. First of all, this is bidirectional scanning, and we can see that because look, here is the start point of the scan when we go in this direction, and here is the start point of the scan when we go in this direction. Can you see the intense dots at the beginning of the scan? Now that is not something that I was expecting. I'm expecting these to be uniform all the way along, and in addition to that, although these are very, very thin lines, these are a lot thinner than 0.06, because look, 0.06, how many of these lines do you think I could get between these two? The answer is at least 2 of them. So that means that probably this line here is about 0.03 thick. So that's the great advantage of knowing the scale of this picture. 0.1 long and 0.1 pitch wide. Well, you can look and say that the lines are already longer than 0.1 because, first of all, look, they overlap with each other. So something strange going on here with the timing and with the power. And we can see also that we've got a halo around the outside of each of these. So let's just push on a little bit. Well, let's just go back a little bit because I have seen something earlier. That's at 800 kilohertz. And that is CW, continuous wave mode, and those look to be approximately what we expected, about 0.065 long, with little bits on the end that sort of just about overlap each other. So that's pretty representative of what I was expecting, if you remember, when I looked at the picture beforehand. That there is 800 kilohertz at 2 nanoseconds. So that's more or less one of the numbers that I'm allowed to use for peak power. Right, so that's 2 nanoseconds, 850 kilohertz. And this is 800 kilohertz at 2 nanoseconds. Look at the width of the line difference between this and this. These are both set at exactly the same focus point. Okay, so this is CW, or this is 2 nanoseconds. Time shouldn't make any difference. Basically what's happening here is we're only just making it to the most powerful part of the center of the beam, and that's the part that's doing the drawing of this line. Whereas here we've got more time, and so consequently what's happening is we're allowing more of the beam width to do the burning. It may be at a lower power, but it's still being allowed to burn further up the Gaussian distribution shape of the beam. Let's go back to the 8 nanosecond. Where's my dashes gone? Where have my dashes gone? Ah, there they are. They're very thin, but they've also got ghosting around them, you'll see. And they have got a little bit of heavy spot at the beginning of the burn. The beam is getting a bit thicker. Now look what's happened there. First of all, we've got a very distinct white patch at the beginning of every burn, and then what we've got a, well, you can see we've got a little deep black bit in the middle there, which I think is probably burning right the way through to the aluminium underneath. And you'll also note it's got a yellow tinge to it as well, which to me would indicate that we're melting the aluminium oxide. So let's push on. That was at a frequency of 600 kilohertz with 8 nanosecond pulse. Oh dear. We've got a pretty significant burn all the way across there and no dashes. Where have my dashes gone? And there it is again. Look how yellow it is. Dropping down from 200 to 100 kilohertz, we've got our dashes back. Nothing else has changed. Now, I was convinced that I had got a problem with my programming. So I've been in and I've checked my program. Everything is exactly as I expect it to be on every one of these. Having found that these tests have not exactly gone quite to expectations, I've got to question whether or not, first of all, I've been programming them right. And the answer to that question is I'm absolutely sure that I must be programming them right, because some of the results are working perfectly fine. And when I look at my program, everything is consistent throughout the program. All I'm doing is changing basically one number at a time. It's either pulse width or pulse frequency. The power is always 100%, and the scan speed in this particular instance is always 250 millimeters a second. There's something strange about pulse frequency, because when we look at 300 and 400 kilohertz, that's where we seem to be getting most of the problems. I'm absolutely sure it's not the XY mirror system that's at fault, because the mirror system is rotating at a steady speed, whatever that speed is. And it doesn't go click, 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 click to make my dashes. It's going at a steady speed, and the laser itself is switching on and off at a frequency which causes those dots to happen. So there's some sort of problem between the control software and the firing software, where this is a unique problem to this machine because it's got a problem, I can't say. But what we are going to have to do is to get Lotus Laser involved and make them aware that I've got an issue. So even though we've come across this problem, it's not going to stop us investigating one or two other things that we've found today. I am particularly interested in trying to find out how pulse width and pulse frequency can be used and manipulated to generate specific amounts of power, and how that power goes down into the job. Now, when I say power, we're talking about light energy. We're talking about light intensity, stimulating atoms, remember. So when I use the word power, that's what I really mean. But never forget the fact that it's stimulation of atoms that's causing the effects that we're looking at. Now, we can obviously regulate the power to bring it back down to whatever. But I've used 100% today, and I've used a standard scan speed of 250 millimeters a second, which, as I said, is 1/8 of the maximum that this machine can deliver. But different speeds are going to produce different results when we combine it with pulse frequency and pulse width. And that's the strange relationship that I want to try and take a quick look at, because there's some very strange but simple maths involved. Now, throughout this example, we're going to use my little 0.1 millimeter long line as our reference to do some calculations with. Now, as I said, we were doing these tests at 250 millimeters a second. And therefore, it's fairly easy to calculate that 1 millimeter of travel at 250 millimeters a second takes place in 0.004 of a second, or 4 milliseconds per millimeter. Okay, so therefore my line is actually 0.1, a tenth of that travel, so it's going to take 0.4 of a millisecond to travel 0.1 of a millimeter. So if I'm going to produce that line with a pulse repetition rate of 1000 kilohertz, that basically is 1,000,000 cycles per second. So if I take 1 second to divide it by 1,000,000, I finish up with 1,000,000th of a second. So it didn't actually take Einstein to help us with that bit of the equation. And now for the next bit, this is just as simple. If we take the time to travel 0.1 of a millimeter, which is 0.4 milliseconds, and the time it takes to complete one cycle or one pulse, 0.4 milliseconds divided by 1 microsecond, which, when you mess around with the maths and the numbers, it comes out to 400 pulses per 0.1 of a millimeter. So if we go to the other extreme of my test, where I was using 5 kilohertz, there it means if we take 1 second to divide it by 5,000, we finish up with a cycle time for just one cycle of 0.2 milliseconds. So therefore, when we're travelling 0.1 of a millimeter at 5 kilohertz, we're only getting 2 pulses per length of line. We're getting 400 pulses in the line when we do it at this speed, and 2 pulses when we do it at this speed. Okay, now let's put those numbers into a little bit more of a reality check. The very first test that we did was using a 2 nanosecond pulse. So we worked out that at 5 kilohertz, each pulse, each cycle, was 0.2 milliseconds. Right? But at the speed that we're travelling, we're doing 0.4 milliseconds over the whole distance. So there's our whole distance of 0.1 millimeters. And there's our time to do half of it, because we're getting 2 of those pulses per 0.1 of a millimeter. So we've got a time for one pulse of 0.2 milliseconds, but we're actually using a pulse at the beginning of that there, and another pulse there, and another pulse here, which is actually only 2 nanoseconds wide. So how many of these 2 nanosecond pulses could we get in 0.2 of a millisecond? Well, the answer is 100,000, just by this very simple bit of maths. 2 milliseconds divided by 2 nanoseconds. But really, we're only going to put one pulse into that period of time, and it's there and there and there, regardless of how many other pulses we could get in between. So that means that we've got 1 part in 100,000 when we're heating the material, and then 999,000 when the beam or the power is off. So that's a very, very large cooling rate in relation to a heating rate. And that heating ratio is very important to us when we're dealing with pulses. We're no longer working, as we were with the constant wave laser machine, a continuous power. Here we've got little teeny weeny pulses, and we've got a heating effect and a cooling effect. And that's the huge ratio between the two. So when we're working at 1000 kilohertz, we worked out that the pulse rate was 1 microsecond, a millionth of a second, per cycle. So here we are, we've got all these millionths of a seconds, and in 0.1 of a millimetre, we've got 400 pulses. But it does mean to say that we've still got 2 nanoseconds for this pulse, and then 1000 nanoseconds later, we've got another pulse, and then 1000 nanoseconds later, we've got another 2 nanosecond pulse. So that's a ratio of 2 nanoseconds per 1000 nanoseconds, which is a microsecond. And when you do that very simple calculation, it's 500 to 1. So that's the staggering difference between these two frequencies for the same pulse duration. Okay, that's the one thing that you've got to remember. We've got a beam which is roughly 0.06 diameter, 60 micrometers diameter. So if we divide those 400 pulses equally amongst that 0.1 millimeter, we shall find that actually we are going to advance 0.25 microns per pulse. So what that means is we're going to get these pulses which are overlapping by a very, very large amount. In other words, this dot is only going to move forward a small amount, and it's going to almost stand on the same spot, repeating itself. So that's how we're going to get our heating effect, because we're not moving very much for every step of the pulse advancement. Well, it's pretty obvious really when we look at this situation, because we've got a 0.6, 0.06. I mean, by the time we get to here, we will have already covered roughly 0.1. So we've only got 2 pulses, as we said, in this 0.1. So not only have we got a huge off time in relation to the on time, we've got a huge step difference. So we're going to get virtually no repeat heating on top of the one that we put down before. This is all very clear in my mind how this is beginning to work, this machine, and I hope I'm not befuddling you with the numbers. You can go away for yourself and maybe think about this in a bit more detail. But what I am slightly worried about is the inconsistent results that we're getting, and why. Bear in mind these two results are both for the same pulse width, 2 nanoseconds, and the only thing that we're changing here at the moment is the frequency with which we're dispensing these pulses. So in this instance, not only have we got a much better heating to cooling ratio, we've also got a much closer over burning of the dots, so we're going to get a much greater heat build up because of it. Remember, I keep talking about vibration of molecules and atoms. If I vibrate a molecule or an atom with a beam of energy, it's not going to vibrate on its own. It's going to nudge and vibrate its neighbours. And nudging and vibrating its neighbours is basically conduction. We're going to vibrate those molecules into a hotter state because they're going to get excited. And that's how conduction happens through the material. So the other thing that we've got to take into account when we talk about pulses is the fact that some of these pulses are long and shallow. Just because a pulse is 350 nanoseconds long, it isn't necessarily the same power throughout its pulse length, whereas the shorter pulses tend to be just a spike of energy. There are these few in the middle here, which are a mixture of a spike of energy and a certain amount of, let's call it a body energy. So it's yet a further complication that we've got to take into account when we try and choose a waveform, which is why it's so important to try and see and understand what the relationship between damage and frequency and pulse length is. One other rather interesting thought crossed my mind as I was doing those very simple calculations And that is, if we are running a 0.1 line at 2000 millimeters a second with the slowest pulse possible, when we tell the pulse to stop, that's the last pulse, remember, and the last pulse is on its way and it will carry on for another 350 nanoseconds. How far is that 350 nanoseconds going to cause my line to overrun? I'm going to make the line longer by 350 nanoseconds. It's a small point, but it's something that I really want to just build into my equation. Is it important or is it not important? My very basic maths, and I'm going to ask the question in this way so that everybody can understand it. How many 350 nanoseconds chunks are there in 1 second? And the answer is 2.8 million. If we travelled at 1 metre a second, the distance covered in 350 nanoseconds will actually be just one of those chunks, i.e. it'll be 1 metre divided by this big number that we found here. And the answer to that question is 0.35 micrometers, 0.35 microns. So therefore, at 2 meters a second, we're going to get an overtravel of 0.7 micrometers. It's negligible amount. When we do our line, we've automatically got half a beam width hanging out the end. So a tenth of that beam width isn't going to make a lot of difference. It's just a simple piece of information that I can now put to one side and say the beam length and the overtravel has no effect on this at all. But what I'm a lot more concerned about when I look at these pictures is why, from all the theory that we dealt with up to now, technically we should have a fairly steady stream of energy coming out of the laser. Why is it that when the laser switches on, it goes and does 1 power, and then as it gets into its stride, it either goes heavier or in some cases lighter? I haven't yet worked that out because I haven't studied the patterns enough. The one thing that we can always say is that there is a different power at the start of the beam. And you might say, well, that's because, remember, the pulse width looks like this. Therefore, it will always have a starting point which is very sharp. Yes, but what you're forgetting is that we've got 400 of these in that, like that. So there is no reason to have that spot there any heavier than the rest of the line length. So I've got quite a lot of questions, technical questions, which I'm not sure whether Lotus Laser can answer, or whether this is stuff that's got to go back right to people like JPT, who probably won't even want to tell me. So I'm going to gather together some data and send it off to Lotus Laser, and we shall have to put things on hold for a little while until I can come up with some reasonably satisfactory answers to these questions. If I just want to go blub 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 with this machine, it does a fine job, and that's what it's designed to do. I'm not trying to find out how well it does that. I couldn't care less. What I want to find out is how it works. And at the moment, I found my little simple test has shown me that there are conditions under which this system does not work in the way in which I expected. And on that note, I think we shall finish, and I'll go and get myself another cup of coffee, and I'll catch up with you in the next session, whenever that is. Cheerio now, and thanks for your time.